Welcome, everyone. Today we're diving deep, literally, into the world beneath our feet. And no, I'm not talking about your neighbor's sketchy basement renovation. We're talking about ground intelligence redefined, bringing high-resolution vision to the subsurface. Think of this as giving the Earth an MRI, except instead of finding out why your knee hurts, we're figuring out if the ground under your billion-dollar building is going to stay put. So buckle up. This is going to be a rocky ride. See what I did there? All right, let's talk about why dirt is basically the most dramatic diva in all of engineering. You see, soil doesn't follow the rules. It's the rebellious teenager of the material world. Check out these 3 fun facts about why geotechnical engineers have trust issues. Non-linear relationships. Soil behavior doesn't follow simple rules. It's not like, if I push twice as hard, it compresses twice as much. Nope. Soil is more like, oh, you pushed? Well, now I'm going to do something completely unpredictable, because I'm feeling quirky today. Inherent noise. Field data is naturally variable and imprecise. Every measurement comes with more static than a 1990s cell phone call. You drill a hole, take a sample, and it's different from the sample 3 feet away. It's like trying to predict the weather by licking your finger and holding it up. A priori difficulty. This is engineers speak for we literally cannot write down the math before we see what happens. It's like trying to write a recipe for a dish you've never tasted, made with ingredients you've never seen, using cooking methods that don't exist yet. So, yeah, the gap between our beautiful theories and messy reality? It's wider than the Grand Canyon. Ah, yes, the good old days. And by good, I mean terrifying. Let me paint you a picture. It's 1985, you're a geotechnical engineer, and your most advanced technology is a clipboard and illegible handwriting. That coffee-stained borehole log you're squinting at, that's your entire database. Let's break down this nightmare into 3 convenient categories. Accuracy. Manual interpretation is error-prone, and by error-prone, we mean, remember that time someone misread a 6 as a 0 and a building settled 3 feet? Human error isn't just possible, it's probable, especially after the 3rd cup of coffee and the 5th borehole. Efficiency. Analysis is slow and labor-intensive. We're talking weeks to analyze what modern systems can do in hours. It's like using a sundial to time an Olympic sprint. Risk. Predicting failure remains a challenge. Actually, challenge is putting it mildly. It's more like throwing darts blindfolded while riding a unicycle. Sure, you might hit the target, but would you bet your life on it? Because someone's literally betting their life on it. The construction site photo next to that handwritten log, that's where your predictions either hold up or become a very expensive lesson in humility. But wait, there's hope. Enter our technological superheroes. And yes, I know calling AI a superhero is peak 2020's energy, but bear with me. We've got 4 key players in our AI toolbox. Artificial Neural Networks, ANN. These are basically digital brains that learn patterns. They're like that friend who can predict exactly what you're going to order at a restaurant because they've been paying attention for years. Except this friend never sleeps, never forgets, and processes millions of data points for fun. Support vector machines, SVM. Think of these as the ultimate pattern drawing machines. They find the best way to separate good ground from bad ground in multidimensional space. It's like sorting M&Ms, but in 17 dimensions, and the M&Ms are soil samples. Deep learning and computer vision. This is how we teach computers to see soil layers in images. Remember those magic eye pictures from the 90s? This is like that, except the computer can actually see the hidden image, and the image tells you whether your building is going to sink. Natural language processing, NLP. This one's my favorite because it reads those terrible handwritten logs from 1985 and actually understands them. It's like having a translator for engineer hieroglyphics. Together, these tools deliver unprecedented capability in managing geotechnical data. Translation. We can finally manage all this chaotic dirt data without losing our minds. The best part? AI doesn't replace engineers. It augments them. It handles the mind-numbing data crunching so engineers can focus on the interesting stuff, like high-level problem-solving and making sure buildings don't fall down. Which, let's be honest, should probably be the focus. Here's where it gets wild. We're literally copying your brain to understand dirt. I know, right? The irony is not lost on me. Artificial neural networks are inspired by the neural structure of your actual brain. Those neurons firing in your head right now, making you wonder what's for dinner? We've recreated that digitally to solve soil problems. It's like biomimicry, but for math. Here's the magic: pattern recognition. These networks identify relationships in noise. Remember that inherent noise from slide 2? The stuff that made traditional analysis a nightmare? Neural networks look at that noise and go, "Oh, I see a pattern here." It's like looking at a Jackson Pollock painting and somehow extracting a spreadsheet. Incredible, slightly terrifying, but mostly incredible. Data-driven evolution. The model evolves based on the data provided rather than preset formulas. Feed it more data, and it gets smarter. It's like how you got better at video games as a kid, through practice and repetition. Except this kid can practice 1,000,000 times in the time it takes you to brew coffee. No predetermined equations, no rigid assumptions, just pure pattern-learning intelligence. The network doesn't care about your fancy soil mechanics textbook. It cares about what actually happens in the real world. Okay, time for a visual showdown. On the left, we have linear regression, the straight-A student who thinks everything should be a straight line. Bless its heart. Linear regression sees all those wavy, complex data points and goes, "You know what? I'm just going to draw a straight line through the middle and call it a day." It's the engineering equivalent of trying to fit a square peg in a round hole, except the peg is straight, the hole is wavy, and nothing makes sense. Now, feast your eyes on the right side, the ANN model. Look at that beautiful orange curve. It's hugging those data points like they're old friends. This is what we call actually capturing reality. The ANN looks at the same messy data and says, "I see you, complexity. I respect you. And I'm going to match your exact shape because that's what you deserve." It's the difference between a stick figure and a Renaissance painting. This is why neural networks are game changers. Reality isn't linear, so why should our models be? It's like the difference between describing a mountain as a triangle versus actually mapping every contour. One is simple but wrong. The other is complex but right. And in engineering, simple but wrong has a tendency to become expensive lawsuit. Let's peek behind the curtain and see how this digital brain actually learns. Spoiler alert, it's through repetition and embarrassment, just like us. Picture this. You've got 3 layers in your neural network. The input layer, where data comes in, the hidden layer, where the magic happens, and the output layer, where predictions come out. It's like a very nerdy sandwich. Now, here's the learning process, which I like to call guess, fail, adjust, repeat. Step 1. Input and known output. We feed the network data and tell it what the answer should be. Hey, neural network, this is what sand looks like. Please remember this. Step 2. Prediction and error calculation. The network makes a guess, and we check how wrong it was. Early on, it's very wrong. Like predicting snow in the Sahara wrong. But that's okay. We calculate exactly how wrong it was. Step 3. Weight adjustment. This is the beautiful part. The network adjusts its internal connections, called weights, to be a little less wrong next time. It's like fine-tuning a guitar, except the guitar is made of math, and the music is accurate soil predictions. Then we do it again, and again, and again, thousands of times. Each iteration, the network gets slightly better. It's like training for a marathon, except faster and with more linear algebra. Eventually, after enough repetitions, the network becomes eerily good at recognizing patterns. Feed it new data it's never seen before, and suddenly it's making predictions like a seasoned expert. Except this expert never gets tired, never needs coffee, and never calls in sick. Now, let's zoom out and see where all this AI wizardry fits in the big picture. We're talking about intelligence across the entire project lifecycle, from the first shovel in the ground to monitoring the structure 50 years later. We've got 3 major phases. Phase 1. Intelligent investigation. This is where we're digitizing the ground. Instead of just drilling holes and hoping for the best, we're creating a high-resolution digital model of what's beneath the surface. It's like Google Earth, but for underground. Google Underneath? I'm workshopping the name. Phase 2. Predictive design and analysis. This is engineering with foresight. We're not just reacting to problems, we're predicting them before they happen. It's like having a crystal ball, except the crystal ball is powered by neural networks and actually works. Imagine designing a foundation and knowing exactly how it'll perform before you pour a single cubic yard of concrete. Phase 3. Real-time monitoring. This is about creating living structures. Your building isn't just a static thing anymore. It's constantly monitored, constantly assessed. If something starts to go wrong, we know immediately. It's like having a Fitbit for your infrastructure. Congratulations! Your dam is having a great day. Only minor strain detected. Keep up the good work. This is the future, folks. Intelligent investigation, predictive design, and real-time monitoring. It's like giving infrastructure a nervous system, a brain, and a smartwatch. All right, let's talk about transformation. No, not the new year, new me kind. The taking analog chaos and creating digital order kind. On the left, we have the traditional input, a scanned, handwritten borehole log. Notice the coffee stains? Yeah, those are authentic. That's decades of geotechnical history right there. Smudged, stained, barely legible, and absolutely critical for not killing people. Reading these logs used to be an art form. Is that a 6 or a 0? Is that clay or play? Why is there a phone number in the margin? It's archaeology meets cryptography meets, please don't let this be important. But then, through the magic of OCR and NLP extraction, we transform this beautiful disaster into a structured digital asset. On the right, you see clean, organized data. Depth measurements, soil types, SPTN values, that's nerd speak for how hard the ground is, even a 3D visualization of the soil core. Everything is searchable, analyzable, and most importantly, legible. This is the foundation, pun absolutely intended, of everything else we're doing. You can't run fancy AI models on coffee-stained paper from 1987. Well, technically, you can't run fancy AI models on coffee-stained paper at all because computers don't eat paper. But you get my point. We're taking analog chaos and building a digital foundation. And unlike actual foundations, this one doesn't need rebar. Here's where things get almost magical. You know those CSI shows where they enhance a blurry image and suddenly it's crystal clear? This is the real-world engineering version of that, except it actually works and doesn't make scientists scream at their TVs. Look at this beautiful heat map. We've got 2 boreholes, those vertical lines where we actually drilled and know what the soil is. But what about all that space in between? That's the mystery zone. Traditional approach? We'll just assume it's similar to what we measured. Fingers crossed. Modern approach with ANN. Hold my coffee while I mathematically estimate the entire property distribution across this site. The neural network looks at the borehole data, considers patterns it's learned from thousands of other sites, and generates this gorgeous gradient map showing estimated soil properties. It's like connecting the dots, except the dots are 50 feet apart, and the picture is underground. Notice the color gradient from deep slate blue to terracotta orange? That's not just pretty, it's data. Different colors represent different soil properties. It's a rainbow of geotechnical confidence. Is it perfect? No. Is it infinitely better than guessing? Absolutely. We're literally seeing the invisible. And if that doesn't make you feel like we're living in the future, I don't know what will. Pop quiz. You're on a construction site, and someone hands you CPT data. CPT stands for Cone Penetration Test. Basically, we shove a cone-shaped probe into the ground and measure resistance. The data looks like a seismograph had a seizure. Squiggly lines everywhere. Now, quick, is that sand, silt, or clay? If you're manually interpreting this, congratulations. You're spending hours staring at squiggles like you're trying to read tea leaves. It's tedious, it's error-prone, and honestly, there are better ways to spend your Friday. Enter Automated Soil Characterization. We take that raw CPT data, left side, yes, those chaotic plots, run it through a neural network, middle, where the digital magic happens, and boom! Out pops a clean, ANN-generated soil profile, right side. Sand, silt, clay. Clearly labeled, accurately classified, faster than you can say geotechnical engineering is surprisingly complicated. The neural network has been trained on thousands of CPT profiles and their corresponding soil types. It knows the patterns. It recognizes that certain resistance signatures mean sand, while others indicate clay. It's like having a soil whisperer, except the whisperer is a computer and never needs lunch breaks. What used to take a trained engineer hours now takes seconds. And the engineer? They're freed up to do actually interesting work, like designing solutions instead of deciphering squiggles. Automation isn't about replacing humans. It's about letting humans be more human and less human calculator hybrid.
Welcome to the fortune-telling portion of our presentation. Except instead of crystal balls and tarot cards, we're using neural networks and load calculations. Way more reliable, slightly less mystical ambiance. This is about engineering with foresight, predicting how structures will behave before we build them. Revolutionary concept, I know. Check out these applications. Pile capacity prediction. You're about to drive a giant concrete column into the ground to support a building. Question: how much weight can it hold? Traditional method: educated guess plus safety factors plus prayer. Modern method: AI analyzes soil conditions, pile geometry, and historical performance data to predict capacity with scary accuracy. It's like going from probably fine to 93.4% confident it'll hold 847 tons. Scenario optimization. What if we made the pile longer? Wider? What if we used a different installation method? With AI, we can simulate dozens of scenarios in the time it used to take to analyze one. It's like having a save game function in real life. That didn't work. Let me reload and try a different approach. Automated load calculations. Remember those tedious hand calculations from engineering school? The ones that filled 15 pages and one arithmetic error ruined everything? The computer does those now. All of them. Perfectly. Every time. While you drink coffee and contemplate the meaning of soil cohesion. This is foresight. This is knowing what will happen before it happens. It's as close to time travel as civil engineering gets, and honestly, it's pretty cool. Time to get serious for a moment. We're talking about predicting disasters before they happen. These are the scenarios that keep geotechnical engineers up at night. Landslide susceptibility. Can AI predict where mountainsides might decide to become valleys? Yes. By analyzing terrain, soil properties, rainfall patterns, and historical slide locations, neural networks can create susceptibility maps. Red zones mean maybe don't build your dream home here. It's like a weather forecast, but for gravity-driven soil avalanches. Soil liquefaction. During earthquakes, certain soils can temporarily behave like liquid. Yes, you read that right. Solid ground becomes quicksand. Buildings don't like this. AI models can predict which areas are vulnerable by analyzing soil composition, groundwater levels, and seismic history. It's like having an earthquake's evil twin whisper its plans to you in advance. Tunneling stress. When you dig a tunnel, the ground around it doesn't just politely step aside. It squeezes, shifts, and sometimes throws a tantrum. AI can model stress distributions around tunnels, predicting where problems might occur. We're basically giving engineers X-ray vision to see underground stress before the tunnel is even excavated. These aren't hypothetical scenarios. These are real phenomena that cause real damage and cost real lives. The ability to forecast them, to see them coming, to prepare, that's not just impressive technology, that's potentially life-saving engineering. And suddenly, all this AI stuff doesn't seem so abstract anymore, does it? Here's a wild thought. What if buildings weren't just static lumps of concrete and steel? What if they were alive, constantly sensing, constantly adapting, constantly communicating their health status. Welcome to Phase 3, Real-Time Monitoring and Management, or as I like to call it, giving infrastructure a nervous system. The project doesn't end after construction. That's the old way of thinking. We built it, our work is done, good luck. No, modern infrastructure is monitored throughout its entire lifespan. We're embedding IoT sensors into dams, tunnels, bridges, and slopes. These sensors are constantly streaming data: stress, strain, temperature, displacement, pore pressure, vibration. It's like a Fitbit, but for a dam. Congratulations, your dam walked 10,000... Wait, dams don't walk. Alert! Alert! AI processes these continuous data streams, learning what normal looks like for each structure. Every structure has its own operational signature, its own heartbeat, if you will. And when something deviates from that signature, the AI notices immediately. This enables proactive maintenance. Instead of waiting for something to break and then fixing it, reactive, we can see problems developing and address them early, proactive. It's the difference between changing your car's oil regularly versus waiting for the engine to seize. This is about creating living structures, infrastructure that senses, learns, and communicates. And honestly, that's both incredibly cool and slightly unsettling, but mostly cool. Let's dive deeper into this monitoring magic. We're talking about instant anomaly detection, the ability to spot problems the moment they start, not months later when someone notices a crack. Here's how it works. AI processes continuous data from embedded IoT sensors in dams, tunnels, slopes, whatever you're monitoring. These sensors are taking measurements constantly. We're talking thousands of data points per day. The AI learns the normal operational signature of the structure. What does healthy look like? What patterns emerge over daily cycles, seasonal changes, different load conditions? The AI catalogs all of this, building a comprehensive model of normalcy. Then, when something deviates from that normal signature, even slightly, the AI catches it immediately. It's like having a doctor who monitors your vital signs 24/7 and notices when your heart rate increases 2 beats per minute. Except, instead of your heart, it's a 500-foot dam holding back a reservoir. The dashboard shows real-time monitoring data, alert status, and deviation analysis. Engineers get notified instantly, not next week during a scheduled inspection, not next month when visible cracks appear. Instantly. This detects potential failure signs long before they'd be visible during manual inspection. We're talking about catching problems when they're whispers, not screams. When they're cheap to fix, not catastrophically expensive. When they're maintenance issues, not evacuation situations. This is the difference between reactive engineering, oh no, something broke, and predictive engineering. Something might break in 3 months, let's fix it now. And that difference? That's everything. Now, let's scale this up. Because monitoring one structure is cool, but monitoring an entire portfolio? That's next level. This slide shows a satellite or aerial view with deformation heat mapping. Those colors aren't artistic choices, they're data visualization. We're literally looking at ground movement from space. See that warning? Plus 3.5 centimeters deformation, safety factor 1.2. That's the system flagging a potential issue. 3.5 centimeters of movement has been detected, and the safety factor has dropped to 1.2. For non-engineers, That safety factor is like having $1.20 in the bank when you need to pay a $1 bill. It works, but there's not much margin for error. Traditional monitoring. Someone walks the site monthly, takes measurements, compiles a report weeks later. By the time anyone sees the data, that 3.5 centimeters might be 10 centimeters, and your safety factor might be 0.8, which is fancy engineering talk for uh-oh. AI-powered monitoring at scale. Continuous data collection, instant analysis, immediate alerts. Multiple sites monitored simultaneously. Pattern recognition across your entire infrastructure portfolio. It's like having 1,000 engineers working 24/7, except it's actually just very sophisticated software and a lot of sensors. This is monitoring at scale, not just one structure, but entire networks. Highways, dams, slopes, tunnels, all watched simultaneously. If anything, anywhere starts to misbehave, you know immediately. It's like being omniscient, but only for infrastructure safety, which is honestly the most useful kind of omniscience for a civil engineer. And here we arrive at the big conclusion, the main point, the thesis statement of this entire presentation. AI is not a replacement. It is a powerful amplifier. Let me say that again for the folks in the back worried about robot overlords. AI is not replacing engineers. It's making engineers superhuman. Think about what we've covered today. AI digitizes handwritten logs so engineers don't have to squint at coffee-stained paper. AI interpolates soil properties so engineers know what's underground. AI classifies soil types so engineers don't spend hours interpreting squiggly lines. AI predicts pile capacity, optimizes scenarios, calculates loads. AI monitors structures 24/7 so engineers catch problems early. AI processes massive data sets so engineers can focus on decisions. Notice a pattern? AI handles the tedious, the repetitive, the data-heavy tasks. The engineer handles the creative, the complex, the decision-making tasks that require judgment, experience, and, frankly, humanity. You can't automate engineering judgment. You can't replace the critical thinking that comes from years of experience. You can't eliminate the need for humans to make final decisions about safety, design, and risk. What you can do is give engineers better tools, faster analysis, more accurate predictions, deeper insights, real-time information. That's what AI does. The future of infrastructure is built on a foundation of data-driven insight. But that foundation is designed, built, and maintained by engineers, augmented engineers, with capabilities our predecessors could only dream of. We're not being replaced, we're being upgraded. And honestly, it's about time. Because infrastructure challenges aren't getting easier, and we need every advantage we can get. So embrace the augmentation. Welcome your AI co-pilot, and let's build some amazing things together.